Titanium dioxide, also known as titanium, 4, oxide or titania, is the naturally occurring oxide of titanium, chemical formula TO2. When used as a pigment, it is called titanium white, pigment white 6, or CI 77891. Generally it is sourced from ilmenite, rutile and anatase. It has a wide range of applications, from paint to sunscreen to food coloring. When used as a food coloring, it has E number E171. Occurrence: titanium dioxide occurs in nature as well-known minerals rutile, anatase and brookite, and additionally as two high-pressure forms, a monoclinic baddelite-like form and an orthorhombic I+ or PbO2-like form, both found recently at the Riest crater in Bavaria. It is mainly sourced from ilmenite ore. This is the most widespread form of titanium dioxide-bearing ore around the world. Rutile is the next most abundant and contains around 98% titanium dioxide in the ore. The metastable anatase and brookite phases convert irreversibly to the equilibrium rutile phase upon heating above temperatures in the range 600°-800 °C. Titanium dioxide has 8 modifications in addition to rutile, anatase, and brookite. 3 metastable phases can be produced synthetically, and 5 high-pressure forms also exist. The cotunite type phase was claimed by L. Dobrovinsky and co-authors to be the hardest known oxide with a Vickers hardness of 38 GPa and the bulk modulus of 431 GPa at atmospheric pressure. However, later studies came to different conclusions with much lower values for both the hardness and bulk modulus. The oxides are commercially important ores of titanium. The metal can also be mined from other minerals such as ilmenite or leucine ores, or one of the purest forms, rutile beach sand. Star sapphires and rubies get their asterism from rutile impurities present in them. Titanium dioxide is found as a mineral in magmatic rocks and hydrothermal veins, as well as weathering rims on perovskite. TO2 also forms lamellae in other minerals. Spectral lines from titanium oxide are prominent in Class M stars, which are cool enough to allow molecules of this chemical to form. Production: the production method depends on the feedstock. The most common method for the production of titanium dioxide utilizes the mineral ilmenite. Ilmenite is mixed with sulfuric acid. This reacts to remove the iron oxide group in the ilmenite. The byproduct iron, 2, sulfate is crystallized and filtered off to yield only the titanium salt in the digestion solution. This product is called synthetic rutile. This is further processed in a similar way to rutile to give the titanium dioxide product. Synthetic rutile and titanium slags are made especially for titanium dioxide production. The use of ilmenite ore usually only produces pigment-grade titanium dioxide. Another method for the production of synthetic rutile from ilmenite utilizes the Beecher process. Rutile is the second most abundant mineral sand. Rutile found in primary rock cannot be extracted, hence the deposits containing rutile sand can be mined, meaning a reduced availability to the high concentration ore. Crude titanium dioxide is purified via converting to titanium tetrachloride in the chloride process. In this process, the crude ore is reduced with carbon, oxidized with chlorine to give titanium tetrachloride. That is, carbothermal chlorination. This titanium tetrachloride is distilled, and reoxidized in a pure oxygen flame or plasma at 1500 2000 K to give pure titanium dioxide while also regenerating chlorine. Aluminium chloride is often added to the process as a rutile promoter. The product is mostly anatase in its absence. The preferred raw material for the chloride process is natural rutile because of its high titanium dioxide content. One method for the production of titanium dioxide with relevance to nanotechnology is solvothermal synthesis of titanium dioxide. Nanotubes, anatase can be converted by hydrothermal synthesis to delaminated anatase in organic nanotubes and titanate nanoribbons, which are of potential interest as catalytic supports and photocatalysts. In the synthesis, anatase is mixed with 10 m sodium hydroxide and heated at 130°C for 72 hours. The reaction product is washed with dilute hydrochloric acid and heated at 400 degrees Celsius for another 15 hours. The yield of nanotubes is quantitative and the tubes have an outer diameter of 10 to 20 nm and an inner diameter of 5 to 8 nm and have a length of 1 ai 1/4 m. A higher reaction temperature and less reaction volume gives the corresponding nanowires. Another process for synthesizing TiO2 is through anodization in an electrolytic solution. When anodized in a 0.5 weight % HF solution for 20 minutes, well-aligned titanium oxide nanotube arrays can be fabricated an average tube diameter of 60 nm and length of 250 nm. Based on X-ray diffraction, nanotubes grown through anodization are amorphous. Applications: the most important application areas are paints and varnishes as well as paper and plastics, which account for about 80% of the world's titanium dioxide consumption. Other pigment applications such as printing inks, fibers, rubber, cosmetic products and foodstuffs account for another 8%. The rest is used in other applications, for instance the production of technical pure titanium, glass and glass ceramics, electrical ceramics, catalysts, electric conductors and chemical intermediates. It also is in most red-colored candy. Pigment: titanium dioxide is the most widely used white pigment because of its brightness and very high refractive index, in which it is surpassed only by a few other materials. Approximately 4.6 million tons of pigmentary TiO2 are used annually worldwide, and this number is expected to increase as utilization continues to rise. When deposited as a thin film, its refractive index and color make it an excellent reflective optical coating for dielectric mirrors and some gemstones like mystic fire topaz. TiO2 is also an effective opacifier in powder form, where it is employed as a pigment to provide whiteness and opacity to products such as paints, coatings, plastics, papers, inks, foods, medicines as well as most toothpastes. In paint, it is often referred to offhandedly as the perfect white, the whitest white, or other similar terms. Opacity is improved by optimal sizing of the titanium dioxide particles. Some grades of titanium-based pigments as used in sparkly paints, plastics, finishes and pearlescent cosmetics are man-made pigments whose particles have two or more layers of various oxides often titanium dioxide, iron oxide or alumina in order to have glittering, iridescent and or pearlescent effects similar to crushed mica or guanine-based products. In addition to these effects, a limited color change is possible in certain formulations depending on how and at which angle the finished product is illuminated and the thickness of the oxide layer in the pigment particle. One or more colors appear by reflection while the other tones appear due to interference of the transparent titanium dioxide layers. In some products, the layer of titanium dioxide is grown in conjunction with iron oxide by calcination of titanium salts around 800 degrees Celsius or other industrial deposition methods such as chemical vapor deposition on substrates such as microplatelets or even silicon dioxide crystal platelets of no more than 50 micrometer in diameter. The iridescent effect in these titanium oxide particles is unlike the opaque effect obtained with usual ground titanium oxide pigment obtained by mining, in which case only a certain diameter of the particle is considered and the effect is due only to scattering. In ceramic glazes, titanium dioxide acts as an opacifier and seeds crystal formation. Titanium dioxide has been shown statistically to increase skimmed milk's whiteness, increasing skimmed milk's sensory acceptance score. Titanium dioxide is used to mark the white lines of some tennis courts. The exterior of the Saturn V rocket was painted with titanium dioxide. This later allowed astronomers to determine that J002E3 was the SIVB stage from Apollo 12 and not an asteroid. Sunscreen and UV-blocking pigments in the industry. In cosmetic and skincare products, titanium dioxide is used as a pigment, sunscreen and a thickener. It is also used as a tattoo pigment and in styptic pencils. Titanium dioxide is produced in varying particle sizes, oil and water dispersible, and in certain grades for the cosmetic industry. Titanium dioxide is found in the majority of physical sunscreens because of its high refractive index, Its strong UV light absorbing capabilities and its resistance to discoloration under ultraviolet light. This advantage enhances its stability and ability to protect the skin from ultraviolet light. Nanoscale titanium dioxide particles are primarily used in sunscreen lotion because they scatter visible light less than titanium dioxide pigments while still providing UV protection. Sunscreens designed for infants or people with sensitive skin are often based on titanium dioxide and/or zinc oxide, as these mineral UV blockers are believed to cause less skin irritation than other UV-absorbing chemicals. This pigment is used extensively in plastics and other applications not only as a white pigment or an opacifier but also for its UV-resistant properties where the powder disperses the light unlike organic UV absorbers and reduces UV damage, due mostly to the extremely high refractive index of the particles. Certain polymers used in coatings for concrete or those used to impregnate concrete as a reinforcement are sometimes charged with titanium white pigment for UV shielding in the construction industry, but it only delays the oxidative photodegradation of the polymer in question, which is said to chalk as it flakes off due to lowered impact strength and may crumble after years of exposure in direct sunlight if UV stabilizers have not been included. Photocatalyst. Titanium dioxide, particularly in the anatase form, is a photocatalyst under ultraviolet light. It has been reported that titanium dioxide, when doped with nitrogen ions or doped with metal oxide like tungsten trioxide, is also a photocatalyst under either visible or UV light. The strong oxidative potential of the positive holes oxidizes water to create hydroxyl radicals. It can also oxidize oxygen or organic materials directly. Hence, in addition to its use as a pigment, titanium dioxide can be added to paints, cements, windows, tiles, or other products for its sterilizing, deodorizing and anti-fouling properties and is used as a hydrolysis catalyst. It is also used in dye-sensitized solar cells, which are a type of chemical solar cell. The photocatalytic properties of titanium dioxide were discovered by Akira Fujishima in 1967 and published in 1972. The process on the surface of the titanium dioxide was called the Honda-Fujishima effect. Titanium dioxide, in thin film and nanoparticle form, has potential for use in energy production. As a photocatalyst, it can carry out hydrolyses. That is, break water into hydrogen and oxygen. With the hydrogen collected, it could be used as a fuel. The efficiency of this process can be greatly improved by doping the oxide with carbon. Further efficiency and durability has been obtained by introducing disorder to the lattice structure of the surface layer of titanium dioxide nanocrystals, permitting infrared absorption. In 1995, Fujishima and his group discovered the superhydrophilicity phenomenon for titanium dioxide-coated glass exposed to sunlight. This resulted in the development of self-cleaning glass and anti-fogging coatings. TiO2 incorporated into outdoor building materials, such as paving stones in Noxa blocks or paints, can substantially reduce concentrations of airborne pollutants such as volatile organic compounds and nitrogen oxides. A photocatalytic cement that uses titanium dioxide as a primary component, produced by Atale Cementi Group, was included in Time's Top 50 Inventions of 2008. Attempts have been made to photocatalytically mineralize pollutants in wastewater. TiO2 offers great potential as an industrial technology for detoxification or remediation of wastewater due to several factors. The process uses natural oxygen and sunlight and thus occurs under ambient conditions. It is wavelength selective and is accelerated by UV light. The photocatalyst is inexpensive, readily available, non-toxic, chemically and mechanically stable, and has a high turnover. The formation of photocyclized intermediate products, unlike direct photolysis techniques, is avoided. Oxidation of the substrates to CO2 is complete. TiO2 can be supported as thin films on suitable reactor substrates. Electronic data storage medium. In 2010, researchers at the University of Tokyo, Japan have created a crystal form of titanium oxide with particles 5 to 20 nanometers that can be switched between two states with light. use of the 5 particles could theoretically lead to a 25 terabyte storage disk. Other applications. Titanium dioxide in solution or suspension can be used to cleave protein that contains the amino acid proline at the site where proline is present. Titanium dioxide is also used as a material in the memristor, a new electronic circuit element. It can be employed for solar energy conversion based on dye, polymer, or quantum dot sensitized nanocrystalline TO2 solar cells using conjugated polymers as solid electrolytes. Synthetic single crystals and films of TO2 are used as a semiconductor, and also in Bragg stack-style dielectric mirrors due to the high refractive index of TO2. Health and safety. Titanium dioxide is incompatible with strong reducing agents and strong acids. Violent or incandescent reactions occur with molten metals that are very electropositive, for example aluminium, calcium, magnesium, potassium, sodium, zinc and lithium. Titanium dioxide accounts for 70% of the total production volume of pigments worldwide. It is widely used to provide whiteness and opacity to products such as paints, plastics, papers, inks, foods, and toothpastes. It is also used in cosmetic and skincare products, and it is present in almost every sunblock, where it helps protect the skin from ultraviolet light. Many sunscreens use nanoparticle titanium dioxide which, despite reports of potential health risks, is not actually absorbed through the skin. Other effects of titanium dioxide nanoparticles on human health are not well understood. Nevertheless, allergy to topical application has been confirmed. Titanium dioxide dust, when inhaled, has been classified by the International Agency for Research on Cancer as an IARC Group 2B carcinogen, meaning it is possibly carcinogenic to humans. The findings of the IARC are based on the discovery that high concentrations of pigment-grade and ultrafine titanium dioxide dust caused respiratory tract cancer in rats exposed by inhalation and intratracheal instillation. The series of biological events or steps that produce the rat lung cancers have also been seen in people working in dusty environments. Therefore, the observations of cancer in animals were considered, by IARC, as relevant to people doing jobs with exposures to titanium dioxide dust. For example, titanium dioxide production workers may be exposed to high dust concentrations during packing, milling, site cleaning and maintenance, if there are insufficient dust control measures in place. However, the human studies conducted so far do not suggest an association between occupational exposure to titanium dioxide and an increased risk for cancer. The safety of the use of nanoparticle-sized titanium dioxide, which can penetrate the body and reach internal organs, has been criticized. Studies have also found that titanium dioxide nanoparticles cause inflammatory response and genetic damage in mice. The mechanism by which TO2 may cause cancer is unclear. Molecular research suggests that cell cytotoxicity due to TO2 results from the interaction between TO2 nanoparticles and the lysosomal compartment, independently of the known apoptotic signaling pathways. The body of research regarding the carcinogenicity of different particle sizes of titanium dioxide has led the U.S. National Institute for Occupational Safety and Health to recommend two separate exposure limits. NIOSH recommends that fine TO2 particles be set at an exposure limit of 2.4 mg per meter 3, while ultrafine TO2 be set at an exposure limit of 0.3 mg per meter 3, as time-weighted average concentrations up to 10 hours a day for a 40-hour work week. These recommendations reflect the findings in the research literature that show smaller titanium dioxide particles are more likely to pose carcinogenic risk than the larger titanium dioxide particles. There is some evidence the rare disease yellow nail syndrome may be caused by titanium either implanted for medical reasons or through eating various foods containing titanium dioxide. See also, dye-sensitized solar cell, NOXA, a building material incorporating TO2. Timeline of hydrogen technologies, surface properties of transition metal oxides, references. External links. International Chemical Safety Card 0338, Nano Oxides, Incorporated. Nano Powders, Legit information on titanium dioxide TO2 www.nano-oxides.com. Retrieved November 2008 NIOSH Pocket Guide to Chemical Hazards, the largest CO2 distributor in China. Interview with Chairman Yang Tao by ICOTC. Freshed out over America map, bbc.co. July 30, 2002, titanium dioxide classified as possibly carcinogenic to humans. 2007, A Description of TO2 Photocatalysis, Crystal Structures of the Three Forms of TO2, Architecture in Italy Goes Green, Elisabetta Povolado, International Herald Tribune, November 22, 2006, A Concrete Step Toward Cleaner Air, Bruno Giussani, BusinessWeek.com, November 8, 2006, Titanium dioxide classified as possibly carcinogenic to humans, Canadian Centre for Occupational Health and Safety, August, 2006, Sunscreen in the Sky? Reflective particles may combat warming, titanium and titanium dioxide production data.